Printed circuit boards are like the connective tissue for every electronic product. With the increase in demand and production for electronic products over the past few years, the number of defective boards produced has increased as well. The defective boards need to be tested and debugged in order to fix customer issues. The professional tools required to perform this analysis tend to be really expensive and rather space-intensive. This leads to small-scale repair shops to resort to extensive manual debugging, which can become extremely tiring, time-consuming, and also lead to human measurement errors. That's where Avery Technology comes in. With our team of aspiring engineers, we came up with an innovative solution to tackle these issues. This is vProbe. The vProbe is a simple, portable, and affordable PCB flying probe testing tool accompanied with a fluid and intuitive user interface design. Flying probe testing is an automated measurement method that uses mechanical arms with probes to accurately run a series of measurements and tests. Let us take a closer look at the implementation of the vProbe. The vProbe uses two mechanical arms to run automated tests on printed circuit boards. As for the hardware of the product, we chose to use a base of our product made out of hardwood in order to prevent electrostatic discharge and avoid excessive weight. In order to achieve the three-dimensional movement with each arm, we made use of a total of 6 stepper motors. Each arm is composed of 3 motors, and each motor corresponds to one of the 3 movement axes. The stepper motors are being controlled by the Arduinos positioned at the back. For accurate tracking of the components on the circuit board, we use a clamp to hold the circuit board firmly in place and calculate the coordinates to track the PCB components. We also designed a probe holder to hold the probe securely in place while performing tests. Keeping usability in mind, the probe holder allows the user to easily remove probes and replace them. Moving on to the software side, we first created a mock-up prototype of the user interface with the goal of making it simple, intuitive, and easy to use. This next bit of our video will demo this mock-up. This is our landing page. Here we can run, create, and edit preset tests. We can also view the previously generated reports and switch between automatic and manual modes of testing. By default, the system is in automatic mode. Once we click on a preset test, we trigger a run command and it lands us here. This is the page for automatic command mode. Here, we can control the tests by the use of play, pause, and stop buttons on the left. We view our progress via a progress bar and track the components using the live camera feed of the board being tested and the schematic design of the board, and the corresponding errors if there are any. We can then view a report for the preset test that we just ran by clicking on the View Report button. This is a sample of what a report will look like. If the user chooses to save it, the most recent report will be shown on the top left corner of the landing page under the Past Reports column. Now, upon clicking the Manual Mode button, we land on this page. Here, we can run the tests manually and then save manual steps into a preset in order to automate the future testing of this board. The backend is written in C++17 using a modern object-oriented design. Our project is built using the open source Qt framework. Its cross-platform implementation allows us to support all major operating systems. The backend is divided into 3 components: test plan, execution thread, and serial communication. The test plan class parses user-created files in the form of CSV files and stores them as test entry objects in memory. While in memory, the software can add, remove, or edit entries based on signals from the front end. These objects are converted back to CSV to save any changes. The execution thread translates test entry objects into instructions that Arduino can understand and then set instructions to the Arduino until completion. The communication between the PC and the Arduino is handled by the serial class. This class defines the behavior of the system when things go wrong, such as how long it should wait for a reply and how many command attempts should it perform before indicating that there was a failure. All components of our product are carefully assembled together, but the system can easily be taken apart to recycle its components. The stepper motors and the Arduino boards are repurposed for a variety of engineering applications that require small movement steps. The clamps can be used for circuit board assembly and inspection. The 3D printed mechanical arms were made with PLA, which is biodegradable, and the hardware can easily be recycled as well. Due to the COVID-19 pandemic, Our group has faced few minor hurdles, and with the permission of the instructor have adjusted the scope of our proof of concept demo accordingly. Initially, the goal was to have the software generate a PDF report showing the measured values. However, as of now, we're using a multimeter to show the values. All team members in the group played a key role in our progress. The work was evenly divided, taking into account each of our specialties. Han, Sahil, and Nathaniel worked primarily on the hardware tasks such as design, circuitry, and assembly, whereas Joey, Sheil, and Juan worked collaboratively on the software tasks such as backend, front-end, and the user interface design. The next part of our video shows the demo of our current progress.
I will now run the test plan that will measure the resistance of this resistor, the resistance of this resistor, and the voltage drop across this LED.
The overall cost of the WeProbe proof of concept is around $1,000 Canadian. However, taking future implications and additional costs into consideration, we aim to launch the WeProbe at an initial price of $1,500. This is an improvement compared to other PCB testers available in the market, which have a starting price of $3,000.